See this dirty spot? That's the default position. You can move around. The more you move, which is what makes the flat visible. He didn't get paid near. Neither do I. We ready? Okay, let's get started. Let me have your attention. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speakers. We actually have 4 speakers today. These 4 gentlemen are all colleagues and good friends from the Oak Ridge National Laboratory. They did a project, finished almost a year ago on today's topic, and I think you're going to find it to be very interesting. But first, let me tell you a little bit about these gentlemen. They're all 4. Each one has a PhD in nuclear engineering. Dr. Dan Ingersoll, his doctorate is from the University of Illinois. Gehin is from MIT. And the other 2 gentlemen, Michael Muhleim and Richard Wood, are graduates of this program. And so we are indeed privileged to have them here today. It's one of the benefits of being so close to a major multi-purpose national laboratory such as the Oak Ridge National Laboratory. We can get these guys to come over here easily. And in fact, Dr. Gehin actually teaches one of our undergraduate courses, for which we are very appreciative. So without any further delay, the topic of their presentation today is Innovative Safety Technologies for Advanced Nuclear Power Reactors. Please welcome these 4 gentlemen.
It's a real pleasure to be back here giving a seminar at UT. It's also a pleasure to be talking about this topic, because this is a project that these gentlemen and some colleagues at UT, you may recognize some of those names, participated in. It was a 2-year project, was what we call a laboratory-directed research project at ORNL, which means it was a strategic investment by the laboratory to help us develop the capability to get into a new area of work. So what we're going to do is, I have the pleasure of sort of herding these cast of researchers on several related projects. I'm going to give a very brief overview of what the project was and what the elements are, and then let each of the 3 principals talk about their particular subtasks in that work. I say this was intended to be a strategic investment by the lab. Our strategy at that point was, number 1, to develop and expand our capabilities in advanced reactor design work and technologies that would have general applicability to a whole host of advanced reactors that were under development at this time. And to keep the time frame in mind, this project was started back in the year 2000, when really the nuclear energy took a big boost with the national energy policy. Reactors didn't become a dirty word any longer. And so there was a lot of interest nationwide to jump in and try to restore our capabilities and advance new designs. The other particular strategy that we had in mind with this project was to align ourselves with one of the emerging reactor concepts at that time, and particularly one that we felt had some near-term payoff. And what we did was target our general research towards its application to the IRIS design specifically, which stands for International Reactor Innovative and Secure. I believe some of you who've been around more than a couple of years may remember Mario Corelli, who gave a seminar here 2 or 3 years ago. He really got us started in our involvement with the IRIS project. What we did, what we felt were 3, the strategic theme of our project was essentially safety and reliability for advanced reactor systems. And we, based on discussions at Oak Ridge, we came up with 3 subtopics to that. One was to develop an innovative approach to in situ surveillance and diagnostics of Generation 4 reactors. This was real important because of particularly the long cycle times that the concept developers were striving for would require more online in situ surveillance. A second area is the innovative reactor reactivity control features. These are generally unique beasts, not like the current generation of power reactors, and so coming up with control strategies that would emphasize the features of these designs was important. And then third, to develop a novel PRA tool that could be used not for a detailed, fully engineered design, but could be used at the very early stage of concept development, for which there really is no similar capability. Now, each of the three speakers that will follow will talk about each of those areas in a lot more detail. But I'll just give you a little bit of information on the IRIS project. IRIS started back in '99. It was one of the first round NARI projects. It's formed of a consortium of Westinghouse-led and a number of universities. Within a year or so, Mario Corelli, who's the leader of that project, grew the consortium to about 18 different countries, about 8 different countries, about 18 to 20 different organizations. And we, ORNL, became one of those organizations. It is a class of integral primary reactor systems. That is, the heat exchangers are inside the vessel. Has a tremendous safety advantage in that you can't have a large pipe break locally because there are no large pipes in this kind of system. It uses extensive passive safety features, which is sort of a requirement for the Generation 4 concepts. As I say, we've compiled now, we're losing track, I think it's about 9 countries now, about 20 different organizations. UT has been an affiliate member of that team and working in some related NARI projects. And the project has been quite successful as it is, and it has already moved into some pre-licensing discussions with the NRC, which started last fall. So it's really moved along quickly. It's been an exciting project to be part of, particularly with the international flavor that it has. And as far as our return on investment, I think, in my unbiased position, that it was a tremendously successful LDRD project, because with an investment of about $600,000 over 2 years, it really led us into the win of a NARI project that started last year that will bring $1 million to Oak Ridge, as well as some additional funds to Westinghouse. We also got lined up and are still working toward an INARI with Brazil, who's very interested in IRIS. The NRC immediately took interest in our PRA tool. May talk a little bit more about that. There are several commercial partners that are part of the IRIS consortium, and they've moved from a research program into a commercialization project. I think you'll see a lot of funds come forward from that, of which ORNL should benefit. And in the DOE program called the 2010 program, we're trying to kickstart the nuclear industry in the U.S. to order a plant. At least 2 of the 3 utilities that are participating in that program have included IRIS as the potential design that would consider building early on. So we feel like we picked a good team to be part of, and these 3 guys will show you some of the good research that we accomplished out of that project. Richard, I think you're up next.
It's kind of like Ted Healy and his Three Stooges, but you get to decide which one of us are Curly, which one's Larry, and it has to be Shemp, because Curly did, actually I guess Shemp instead of Curly, because Curly didn't come in until after Ted Healy was gone. That's about all I have to say. We'll move on to the next topic. I left all my innovative research at Oak Ridge. What I'll talk about is in situ surveillance and diagnostics, and you can see the top layer of a cast of thousands that contributed to this program, and I especially want to acknowledge Kerr and Bell for their contributions in this area, especially in the area of fault detection and isolation. I'll talk about the different aspects of the in situ surveillance and diagnostics, but as Dan mentioned, being an integral pressurized water reactor with the steam generators inside the pressure vessel and also the primary system coolant pumps, you have a lot of major components that at conventional commercial power reactors can receive a great deal of access and maintenance over the course of the life of the plant. In this case, your access is limited to when you shut down for refueling, and so you have to maintain knowledge of the status of those large pieces of equipment during the course of the fuel cycle. So, the goal of the task was to develop intelligent, integrated diagnostics and control in an architectural concept that accommodated that integration and allowed for the creation of hybrid control so that information could be extracted and decisions could be made. The need for a system was driven by continuous and autonomous operation of the IRIS reactor over the long fuel cycle, with the goals being a 4 to 8 year interval between refueling outages. Also, as I mentioned, the inaccessibility of key reactor components and the need to minimize unanticipated failures and downtime for maintenance to improve the economics of the system. The IRIS helical coil steam generator was chosen as the focus of the effort because it is unique. In this case, as I mentioned, you have the steam generators that are located inside the pressure vessel. You have the secondary coolants on the inside of the tubes rather than the outside of the tubes, with the primary coolant flowing on the outside of the tubes. So you have some interesting dynamics that come up. This is a once-through steam generator with boiling and then a superheat region. Those Westinghouse, in discussing with them, they identified the helical coil steam generators as the components within the pressure vessel that are of most interest for structural and performance monitoring. So the 4 related efforts that were included in this aspect of the overall project were the development of an architectural framework to accommodate the advanced diagnostics and monitoring system and allow for integration into control. Exploring diagnostic techniques that are capable of automatically checking the integrity of critical systems and reactor components, developing in situ monitoring techniques for the helical coil steam generator, and then combining the results from each of those 3 tasks into an integrated demonstration on a simulated platform. The architectural framework tasks for this effort focused on the communications infrastructure, and the emphasis was on plant-wide use of open system communication standards and making use of wireless technology as it made sense. It included existing and emerging standards for all levels of the communication hierarchy, the 802 family, Ethernet and Bluetooth, the smart sensor standards, and also field bus for the field devices, the sensors and the actuators. It recommended the use of secure wireless data communication where to reduce both capital and maintenance costs. And for the integrated demonstration, we performed the simulation making use of some wireless nodes. The techniques for in situ monitoring of the helical coil steam generator included the development of steady state and dynamic models to generate measurement data for both normal and off-normal condition, representing both off-normal in the dynamic condition of the overall system and also degradation in the field devices. A fault detection and isolation module was developed by Bell and to detect and diagnose both reactor components and sensor malfunctions. And this module was based on data-driven models and rule tables that showed the behavior of process variables for different fault conditions, and the simulation fed in those fault conditions, and the FDI module was able to detect that a fault occurred and then identify what the source of the fault was. And so the dynamic model and the FDI modules were linked, coupled with the wireless communication network that I talked about previously for the integrated demonstration to illustrate how in situ monitoring could occur. This is a block diagram illustrating how the demonstration was put together. On one computer, we had the simulated IRIS reactor component and the field sensors, and this interface is just illustrating the output of the simulation model, which included the process variables and also some inputs so that you could select certain kinds of faults. Those were connected to an Ethernet hub, which was then connected to a wireless transmitter, which communicated to a receiver, which provided the sensor data to the FDI module, which then ran through the evaluation and determined whether or not a fault had occurred, and then identified the source of the fault. And it was set up so that we could have also formed this, allowed other users to participate, but given funding and time constraints, that part was never implemented. And these are some photographs illustrating the equipment that was used in the simulation. So you have the desktop computer that's running the dynamic model, and the laptop computer that's got the FDI module, and there's the wireless transmitters. And if you look really carefully, you can see the transmission. No, I don't think that would be part of the point of wireless communication. But anyway, here's an example of some of the faults that were run through as part of the demonstration. In this case, it's a steam temperature sensor fault. So you can see the fault injection was selected for the steam temperature sensor fault. It's a bias fault. And then let's stand at a different angle so maybe I can actually see it as well. This is the bias that occurs on the signal, a slight offset, and that's occurring. And there's the Q statistic, which is the statistical indicator of the fault. And over here is the identification of the fault. A fault has been detected, and then an identification of, or an isolation of the source of the fault, which is the steam temperature fault. So, a steam temperature sensor fault was injected at the simulation time of 74 seconds, and then it was detected. So this is a previous residual. That's the onset of the fault. So there's the bias that's added, and there's the Q statistic indicating that a fault exists. And this is from a previous fault that was run. It doesn't clear this. It progresses in time, so it doesn't clear the display from previous scenarios. And this is the a little later in time for the same fault, so you can see the bias occurs and the detection, and after it's cleared, then it indicates that there's no longer any fault, so it determines that the fault is cleared. And this is a steam pressure sensor fault example. In this case, it's a drift fault. So at 204 seconds, drift is introduced into the signal coming from the simulated pressure sensor. So out here, there's some drift that's introduced, and you can see the Q statistic is indicating that a fault has occurred, and the result is presented. A fault has been detected, and what's the source? The steam pressure fault. So we ran through all of these in real time using the wireless communication as the path between the simulated reactor and the fault detection and isolation algorithm. And you'll have to trust me because I don't have a videotape of it. But Bell will confirm that it did actually work. And this shows when it's cleared, so you can see that the drift clears from the variable, and the Q statistic clears. So to summarize the accomplishments, we developed an architectural framework, and this was coupled with an integrated hierarchical functional architecture that we had developed under a supervisory control and that we're applying to autonomous control of space nuclear power. But the purpose was to facilitate autonomous operation and the integration with advanced diagnostics and make use of existing and emerging open communication standards. We developed a robust method for in situ detection and isolation of faults for the helical coil steam generator using data-driven modeling. We also did some other diagnostic approaches as well, looking at the process variables. In this case, we were focused on the field devices. And then we demonstrated all these concepts in an integrated demonstration using software simulations and prototypic communications hardware. And so those are capabilities that remain available for follow-on, and we are using some of those things for, as I mentioned, the space nuclear power, because these concepts, while they were focused on the innovative reactor, the International Reactor Innovative and Secure, I need to say that right so I don't say innovative insecure, it's and secure. But we're also using it for the Jupiter Icy Moons Orbiter program as well. And I think we move on to burnable poisons.
All right. Thank you, Richard. I'm going to talk about the burnable poison designs that we came up with for the IRIS reactor. I worked closely on this project with a former student from here, Alan Wallaber, who did a lot of the work. Most of these LDRDs the funding's kind of slim, so we like to tap into universities and other areas to try to get good students and help develop their capabilities and relationships, and that worked out very well in this case. Alan Wallaber did this work for a master's thesis and completed it last year, and did a real fine job. Dr. Ron Peavy also helped out on this. So, the IRIS design goals, as Dan had mentioned, is long life, and the original plan was to have an 8-year life for this reactor and to have what's called a straight burn core for proliferation resistance, meaning you just load the thing up with fuel and you lock it shut and you operate it. So not only do you want to make sure all your equipment functions properly, you monitor, like Richard just talked about, you want to make sure you can get a decent core lifetime. And that introduces a lot of problems because you have to actually load the core with excess reactivity, and you have to control that reactivity in a reasonable way to make sure you actually reach your cycle length, and hopefully not have a penalty at the end of cycle. Now, since the original design, they've backed off of that a little bit and went to perhaps a 4-year cycle now, maybe a 8-year cycle later on, driven not only by reactivity control issues, but also by the 5 weight % limit on fuel that we currently have for manufacturing. And they've also been looking at a 2-batch core to help improve the fuel cycle economics. But nonetheless, they're still very interested in long cycle lengths, and a lot of the work that we did has been factored into that. Now, one thing that's unique about the IRIS, it's safety by design. There's no possibility of local events, and we also have to have passive safety mechanisms. So that means whatever design actions we take with the core, we have to make sure that we have negative reactivity coefficients, things like that. It has to be passively safe. And like I mentioned, we had Ron Peavy and Alan Wallaber work very closely with us. Okay. So our goals for this work were to assemble a set of tools that we could use for advanced reactor analysis. A lot of the work that we had done at Oak Ridge has not been on core systems like IRIS. They've been on more advanced core designs like the advanced neutron source and research reactors and odd beasts compared to a power reactor. So our goal was to take a set of tools, put them together that we can do a good job on essentially PWR design. We wanted to sharpen our expertise on reactivity control issues, look at different burnable absorbers. We actually had a previous NERI project that looked at advanced burnable absorbers, and we wanted to take some of that expertise and apply it to the IRIS reactor. We want to become a value part of the IRIS team, which I think we did. And one of the original design goals was to eliminate the need for soluble boron. Soluble boron can lead to safety issues if you have boron dilution events and things like that. So part of the goal to improve the safety case was to remove soluble boron. We weren't actually able to achieve that in this step, but maybe in the future. This is a plot of the infinite multiplication factors function of burnup using the standard IRIS type assembly, which is 4.95% and a 17 by 17 lattice. You can see that in a straight burn core, and a core like this is fairly large, so leakage is relatively minor. You've got about 40% in reactivity that you're going to have to control at the beginning of the cycle. And you can get burn up somewhere between 40 and 50 megawatt days per kilogram with such a fuel load. So our goal was to try to flatten this curve so that we can maintain a K affinity or K effective of 1.0. Okay. So now, and of course, in a normal operating PWR today, this is routinely done with soluble boron. You start your reactor with a high boron concentration, and you lower the concentration versus cycle. Like I said, we really wanted to try to design a core that didn't use soluble boron. But partially through on the design discussions, we determined we're probably going to have soluble boron anyway as an independent shutdown margin. So we're going to go ahead and use it, but try to minimize its use as opposed to having high boron concentrations, which can lead to positive moderator temperature coefficients. So that's what we focused on, making sure we keep it as low as reasonably possible and maintain a negative moderator temperature coefficient. Now, some of the tools that we used, and actually the brunt of this work was on Alan because he had to learn how to use all these things and get them to work together, which is a key thing. We have multiple tools that have to work together. One tool is called Helios. This is a advanced lattice physics code developed by Studsvik Scan Power that we have at Oak Ridge. We use it a lot for different types of analysis. It's used commercially to develop core loads for PWRs and BWRs. It's a collision probability code with two cross-section libraries, 45 or 190 groups. It has a lot of geometric flexibility. We use it a lot on BBR systems, which are triangular pitched, as well as square pitch lattices. The user has a lot of control over the solution method, so we can make sure that we're getting very accurate solutions with this code. And we've used it, in this case, to look at single assembly designs, to look at the effect of different vulnerable poisonings, and also to generate cross-sections for core design purposes. Okay, we have another code that we use called Nestle. This was developed at North Carolina State, which is one of our other 4 universities at Oak Ridge that we work closely with. This is a diffusion code. It's a nodal diffusion code, pretty much what's used in industry. Allows a few more energy groups than what normally is used, but same concept. We used Helios to generate the cross-section, like I just mentioned, and used either 2 or 4 energy groups. So a lot of the work in a LWR can be done with 2 energy groups with 4 as a backup to make sure your approximations are okay. And then we can do different searches, search on K effective equals 1 to find the critical boron level, things like that. And this code can be used for basic core analysis, fuel cycle design, and transient, so that we didn't get into the transients in this work. And the other computer code that we used, also developed at North Carolina State, is called Formosa P. This code is used to develop optimized core designs to determine the fuel loading requirements and fuel locations that give you a flat power profile and maximize the cycle duration. And so the purpose on using this code was to take some of the assemblies that we designed with Helios and have Formosa decide where to put them. And I got a few details on here. Cross-sections from Helios, has thermohydraulic feedback, and it has different objective functions you can apply to your optimization. Okay, so what we did, mainly what Alan did with me looking over his shoulder, was to investigate assembly designs to obtain some candidates for core design. So we used Helios just on a single assembly case and looked at a various number of burnable absorbers with different concepts in mind, ranging from just boron rods, which burn straight out, to things that are maybe mixed absorbers where you might have one burning out while another one's building up to try to get longer reactivity control. Once we selected some candidate assembly designs, then we did some core design calculations to see how the core would perform with different reactions. Here's an example of some single assembly calculations performed with gadolinium. We looked at like I said, boron, gadolinium, erbium, and a whole list of other absorbers, and we found that the best prospects for these long-lived cores are gadolinium and erbium, which are now making their way into common use in power reactors for extending their cycles too. The goal in this study was to try to obtain a flat K-infinity profile versus cycle length. The red line on here pretty much achieves K-infinity equals 1 over a large range, and without much penalty, meaning if you look at about 40 megawatt days per kilogram, you see that the red line converges closely to the case without any verbal absorber. So gadolinium is a nice absorber because of the low reactivity penalty. You do have to lump it. Depending upon the loading that you put in, you want to lump it to take advantage of the self-shielding that gadolinium gives you, being a thermal absorber. Now, if we look at erbium, erbium behaves differently. It's a resonance absorber. When you use erbium in your core, you do not need to lump it. You can spread it around more freely and rely on resonance absorption as the means of burnout. The problem with erbium, as you can see at the higher burnups, and compare all the erbium lines, blue line that does not have any erbium at all, there's a pretty large reactivity penalty at the end of life. So that will translate into economic penalty in terms of fuel cycle length that you'd like to avoid. Now, we've had some work at Oak Ridge and looking at using enriched erbium, and that's a possibility to solve that, but there'll certainly be some difficulties to address there. Okay, like I just said, the sort of the ideal gadolinium, however, requires a pretty large loading, 21% by pen, because we need to lump it so it doesn't deplete too fast. In practice, you probably can't get over 10% per pen because you need to maintain the thermal conductivity of the fuel and the fuel material properties. The temperature coefficient, the density coefficient is acceptable with these lower loadings for the assembly case. Erbium ideal is 104 pins on a 17 by 17 array at a fairly low density, 7% per pin, which is acceptable. But we get this 6 megawatt day per kilogram penalty. And positive MDC is acceptable because if you reduce density, that means the reactivity goes down. Negative temperature coefficient. So we're okay there. Now, core studies, we looked at two designs, one with gadolinium, one with erbium. Simulated a two-batch core, which is more the approach that IRIS is going to now, and looked at the impact on the soluble boron in core lifetime. This is what we call the boron letdown curve. It's essentially the variation of boron as a function of burnup, and the boron level starts at the beginning cycle about 1200 ppm and tails down to zero at a cycle length of about 26 megawatt days per kilogram. 1200 is slightly lower than what's used today at current generation. If we use erbium, since we can distribute it more, it's a little bit more effective at lowering the boron concentration. Although in this case, we probably have the core a little bit too heavily loaded because it's hurting us on cycle length more than probably what erbium should. The cycle length in this case is about 18 megawatt days per kilogram burnup. If we back off of the erbium loading, we can increase that to somewhere around 20, but we still have a penalty. Okay, so the design, the use of erbium can improve the boron concentration, and one of the goals that we had to reduce the boron concentration. The erbium, though, has this penalty to end of life. We expect, looking at the power profiles that we achieved with the erbium design, since it's spread more uniformly throughout the core, we have better power peaking profiles. And at the time that we did this, we stated we need to look a little bit more at the safety parameters, the reactivity coefficients, because the concern with gadolinium is that you can get positive moderator temperature coefficients. And if you have higher power peaking with the gadolinium, you can actually have boiling and other problems in the core. So based on some of the studies, the actual core design that Westinghouse is looking at right now employs erbium as their burnable absorber. So it's provided some feedback into their design process. Okay, so conclusions, one of the major things that we did is we assembled this Helios Nestle Formosa methodology and actually utilized it on a real core design. We're using this methodology now related to the NERI that Dan mentioned at the beginning on the pressurizer, where we're going to do coupled 3D neutronics using cross sections of models based on this. extended our analysis capability at Oak Ridge to include advanced nodal methods and these optimization techniques. And we feel we're contributing to the advancing iris core device. Okay, that's
I'm Mike Muhleim, and working on developing a risk-based design optimization tool for iris. How many people in here are familiar with PRA, probabilistic risk assessment? Not too many students, so okay. Well, what we're doing on the iris plan is they're already using a safety by design approach. That is, they're trying to design out the severe accidents that can happen, design them out so they don't happen. No, you can't see it. I think you used to have a picture on it, but the steam generators are inside the reactor vessel. So by doing that, you eliminate a lot of the large break loca accidents that they can't happen anymore. I don't have the big pipes. Westinghouse is also using probabilistic risk assessment, or PRA, during the conceptual design. Well, what I'm going to show you is how powerful it can be when you couple a safety by design approach with a risk-based design approach. So before we can start trying to couple these two, we need to figure out what exactly do we want to accomplish with this approach. So we need to define our objectives. What do we want? Well, we want to be able to assess the baseline reliability, cost, and safety. We want to focus our attention on resources where it matters most. We want to be able to measure the impact and improve the consistency of the different design trade studies. When we do different design concepts, we want to measure the sensitivity, uncertainty, and appropriateness of the models. We want to be able to change the models and see how well they work. And we want to make the PRA insights observable to non-PRA analysts, such as designers and managers or department heads. So first we want to look at, it is ambitious. So first we want to look at how are things done now, and what are we going to have to do to change it? Well, typically, PRAs aren't well suited for design. That they're more on a safety and reliability. And the way they start out with the design, and you use more simplified methods. And then as you go along, at some point you'll have a freeze point in the design, and you'll do a PRA, and by freeze point, I'm just taking a snapshot of what the plant looks like then. The designers don't stop. And say at a 50% design, I'll come back 4 to 6 months later and tell them, hey, back here, this is what I found. These are the problems you have, and you need to work on that. So they're making changes to something that they've already changed quite a bit, and they go on down. Well, what you want is to be able to continuously evaluate where you are in the reliability and risk. So we want to be able to identify the risk drivers as the design develops. So to maximize the design, we need to be able to look at all of the different concepts and change the components and the system arrangements in various combinations for all of the different initiating events. So to do that, we need to be able to retain all of the previous design concepts. And we need to be able to make changes between these different design alternatives, so it'll be pretty easy. And we did this on the iris plan. So we developed a one-button architecture to make it as easy as we can on changing out systems, components, whatnot. Our different designs, we can change component choices, we can change type, sort of like air-operated valve, motor-operated valve, pneumatic valve. We can change out the pumps, like a motor-driven, turbine-driven, diesel-driven. We can change the failure data or the system architecture. We could have a 2-loop system, 3-loop. We could have cross ties between loops. We could change the pumps in there. We could change the valves, all with just a click of a button. in our figures of merit is Jess had talked with the aging, that 4-year refueling cycle, we're worried about the aging effects. We want to be able to measure the reliability. But now, since it's so easy to make design changes, that we can now start looking at comparing metrics, like looking at cost versus reliability. Like I make this design change, it might have a big impact on cost and not much on reliability. I can start making those kind of choices. And the uncertainties and sensitivity, of course. So how do we do that? Well, we have a drop-down menu. And from the drop-down menu are all the different design choices, and all you have to do is just go click on whatever design you want. If you want to change a valve here, I changed it to motor-operated valve. It's initially closed in automatic depressurization system. What the program does, it takes the fault tree module, and the fault tree identifies my system failure modes. It will take the module for that one component that I just chose. It'll insert it into the PRA that has the entire plant failure modes for all its systems and all its initiating events. It'll relink all the support systems. If I change from an air-operated valve to an electric valve, I need to change from air to electricity. It'll do that. It'll readjust my common cause failure probability and recalculate my parameter of interest. So we see with this that we've retained all our design options. We've made changes easily. It's real easy to make changes, and our results are immediate. That we could tell right away whether the system got better or worse, and we could tell why. So we can now start truly optimizing the system. So we applied this to the Iris plant, and the two systems we looked at were the automatic depressurization system and the emergency heat removal system. The ADS, it has two parallel paths to blow down to the suppression pool. And the emergency heat removal system, there are 4 loops. 2 to 4 loops are required to remove the decay heat depending on what the initiating event is. And it's a pretty elegant system in its simplicity, that it removes the heat from the steam generator, dumps it to a refueling water storage tank, have a main loop and a bypass loop, and it goes back to the steam generator. So it is really elegant in its simplicity. That to get it to work, all you have to do is open just either one of those 2 air-operated valves. That's it. So by either one having to open, that means both valves have to fail for that loop to fail. So you look at it and say, well, that's a pretty simple system. What can I do to make that better? But with our design options, we have, again, what was shown, what they had originally were the air-operated valves. And I just go down to my scroll-down menu, click on a motor-operated valve, and it'll change one of them. And then I have to go back in again, because I can change any valve in any order. You know, it doesn't matter what order, I'll still get the same answer. I don't have to change it. I can change to a motor. But in this one, I changed both airs to motor-operated valves. It's just click on the design option you want, and it immediately gives you an answer. So what did we find? We found that the design of the emergency heat removal system was a good design. Of course, there's not much that could go wrong with it. It's just those 2 valves. But we looked from this, we could see that the common cause failure of those 2 air-operated valves was driving the system failure. So since it's so easy to change out the valves, we changed them to motor-operated valves. By changing the motor-operated valves, we reduced the system failure probability in half, just by changing the valves. So we went and looked, and it's still the common cause failure is driving the system failure, but now it's common cause failure of the motor-operated valves. How do you reduce common cause? Common cause would be like a guy going out and doing maintenance on the air-operated valves. He makes a mistake on this valve, then it goes over to this valve, makes the same mistake, and it fails both of them. So that's a common cause failure of the valves. And it's more likely with the air than the motor. So to get rid of the common cause, we change the valves. We make one an air, one a motor.
It's not mine. Keep going, Mike.
It's our fearless leader. Yeah, maybe we should have kept him in line instead of him keeping us in line.
He's going to dance later.
He's gonna dance.
Okay. What else did we learn? Well, we learned that just a few component choices, which in this case we had 11 component choices. We had automatic depressurization, we changed the number of loops, we changed the sizing of the valves. We took the block valves, we could have them initially open, initially closed, and an emergency heat removal system, we switched off the air and motor operated valves. Just these 11 different component choices gave us 160 different design alternatives. So these were 160 different designs that we could evaluate just by clicking a button. We also learned that the logical, or what appears to be a logical choice for optimizing a system without actually evaluating it could be the wrong choice. If we look at the two air-operated valves, this is the combined failure probability of the two air-operated valves. And those air-operated valves, the Westinghouse designers chose those on purpose. And this is the reason why. The combined failure probability is an order of magnitude less than the motor-operated valves. So they said, I have a pretty simple, elegant system. I'm going to put in the best valves I can. And they put in air-operated valves. Well, what we found was by going to the more unreliable valve, the valve that's going to be more likely to fail independently, cut the system failure probability in half.
What's the unit on that vertical scale here? Failure
On this one?
probability? Yeah.
Oh, it didn't show up on it. This one's a 10 to the minus 6, I believe. So 1 times 10 to the minus 6 is for the two air-operated valves. They're 10 to the minus 3 each. And then these are 3 times 10 to the minus 3 each. So
The other diagram?
this one, I believe that's a 10 to the minus 6 too. And what's driving this is that common cause failure of the valves. That it's much more likely that you have a common cause failure of the air-operated valves versus the motor-operated valves. And that's why just looking at something individually can lead you to the wrong answer. You need to look at the whole picture when you're looking at the design. So what did we find? Our main conclusions are we found that just a few number of design alternatives, design choices for components or systems can allow you hundreds of different design alternatives to be evaluated. By learning on the EHRS system, changing out the valves and how to reduce the common cause, and we did that with the automatic depressurization system over there, that we had a 2 order of magnitude reduction in our base case core damage frequency for the IRIS plant. And then Westinghouse took this information that we learned on IRIS and went ahead and applied it to the AP1000, and they're expecting a final design approval in a year. So it's really unusual to go ahead and make a design change this late in the process, but they did because it had such a big impact. So and we expect to have similar results when we go through looking at external events, which are seismic, fire, and flood. We just looked at the internal events right now. And I believe that's it.
Okay. All right, we have time for some questions and comments. A few questions. Art?
Yeah, the steam generators.
Who's the question for?
Pardon?
Which speaker?
Anyone that can take it. The steam generators are stuck in the vessel to eliminate the probability of a large break load. What is the probability for a large break load in the existing
Less than 10 to the minus 6.
It's way less than 10 to the minus 6. I mean, what's the if we don't know the probability of a large break load, what's the probability of a loss of vessel?
Well, you can't look at just again, it's the same thing. You just can't look at the probability of pipe break all by itself. But on the internal events, yes, it is a low probability. But I also have my seismic events, and that's going to start driving up the probability of breaking a pipe.
But a vessel break is about 10 to the minus 8. And essentially, that's what we're showing in the virus is we're coming down fairly close to where that's the next phase. And a large pipe broke load valve, I think, would be higher probability for that.
We don't know what it is, so I've never seen anyone put one. That's why I asked.
Well, when you have your initiated event frequency, yeah, you can have it at 10 to the minus 7, 10 to the minus 8, and run through it. But that was just one example that they do have other, like the small containment is, so if you do get a pipe break, that the pressure in the containment in the vessel will equalize, and then you don't get any flow out because you don't have a driving force anymore. So that was just one example on a passive safety by design that they did. That was one of them. And on my first slide, I used to have a picture, so it was easy to point to that here it is. But there are quite a few things that they use to try to design out the accidents.
Richard, stand up.
Well, I was just going to say I'm not a PRA expert. I'm just recalling from the last IRIS meeting, they were talking about probabilities on the order of 10 to the minus 8, which is what they had reduced their core damage frequency to based on the safety by design and some of the other choices. And they were making note that in contrast to conventional PWRs, now a vessel break was an event they needed to evaluate, whereas for the conventional PWRs, the pipe breaks were the probabilities that were estimated were far higher, so they didn't. That was my understanding from what they were saying.
The double-ended guillotine break of main coolant line is a design basis accident. You have to design your plant to accommodate a double-ended guillotine break, not because of probability, but because it's law.
Right.
Law, yeah.
That's the issue. It's not probability-driven. It's law-driven. I just object to designing plants to accommodate laws because of probability. That's my point.
Yeah.
Okay.
Good.
That airbag.
Good point. Okay, Martin?
Back to the valve issue. What would be the effect of adding a third valve? Better or worse?
Yeah, you'll reduce the common cause slightly, but it won't be a whole lot. So you won't buy a whole lot adding a third valve, because it's usually, if you're going to make a mistake on two, you're more likely that you're going to go ahead and make it on the third one, or whatever is, if it's a design error, whatever. So when you keep adding, like if I had 15 valves in sequence, after my fourth one, I don't have any more benefit. That it's the common cause. If it's going to get 4, it's going to get all 15. So for 3, you'll see a slight improvement, but not a whole lot.
Okay. If there are no more questions and comments, it seems like we always have new faces each week, and I'm glad to see new faces in our colloquium program. And the new people may not know that we sure have refreshments downstairs on the second floor, and everyone is invited. So, and then you can ask more questions from our speakers. They'll be down there. But before we adjourn, let's express our appreciation to these gentlemen for their presentation.
Lee, what's the consequence to a student if a cell phone goes off in class? How many grades did that? A lot.
Hi, how are you? This one?
Maybe.
Oh, yeah,
So I'll just go on down